Hello everyone, welcome to Computer Science E1. This is lecture 4, the Internet Continued. So last time what we were talking about, we talked about a whole bunch of things related to the Internet. We started with a little bit of information on IP addresses and how each IP address is made up of basically 4 octets, or basically 4 bytes of information, so that each octet, as it's so called, or each number in this IP address is 1 byte of information and can store 256 different values. And so total we have about 4 billion IP version 4 addresses. And we talked about how, as a result, we were sort of running out of IP addresses. And in fact, the last block has been allocated a couple of weeks ago now. But despite that, we do actually see that we do have some leeway with these IP addresses through some technologies that have come out, well, not too recently, but have existed for a little while and help us out in this. And we'll talk more about those a little bit later today. So another thing that we spent a bit of time on was DNS, or the Dynamic Name System. So you might hear DNS referred to in a couple of ways. It stands officially for the Dynamic Name System, but a DNS server is another name for that. Could be like a domain name server. And so these are all sort of synonyms for the same thing, for the same system, which is basically like an address book, where you query this server, you give this server a domain name that you want to look up, for example, cnn.com or harvard.edu or what have you, and it will return back to your computer the IP address associated with that domain name. And as you might recall, there can be more than one IP address that can be returned for a given domain name. And we give a couple of reasons for that. Perhaps load balancing is one of them, and for redundancy in case one happens to be unreachable for whatever reason. There's a whole variety of reasons why we might want to do that. And so just to talk a little bit more about domain specifically, domain is something that looks like this, harvard.edu, and specifically it's a word or a phrase, then a period, and then something called a TLD, or a top-level domain. And the reason that we use these, obviously, is that it's a bit easier to remember than the IP address of a given website. So it's much easier to type cnn.com into our browser than it is to type 64.236.16.20, which at the time that I made the slide happened to be one of the IP addresses that they're using. But realize that domains are made up of multiple segments, and one of the segments, sort of the broadest segment, is found in the far right of this, the .edu, and this is called a top-level domain. And a while ago, probably about 15, 16 years ago, there are only a few top-level domains in existence, and you're probably familiar with all, if not, or most, if not all of these, including .com, .edu, .gov, .net, .mil, so on and so forth, .net.org. But this list has been expanded in recent years to allow for top-level domains, or to allow each country that exists its own top-level domain as well. So not only do we have generic top-level domains like .com, .net, .org, .edu, .mil, so on and so forth, we also have TLDs that are specific to countries. So .us, for example, is the top-level domain associated with the United States. .uk is for the United Kingdom. Like we saw last week when we did the trace route to Japan, we had cnn.co.jp for Japan. And there's another one that's actually kind of popular these days, .tv. Does anybody happen to know what country .tv might be from? It doesn't actually mean, .tv doesn't actually mean television. It's actually a country code that's represented up here, and a small island nation of Tuvalu actually owns this domain, and somehow they knew, they were smart enough to realize that .tv might actually be relatively popular, so they allow you to buy domains within their country, within their top-level domain space. So there are registrars, there's people that own all of the domains that exist within each of these country codes, and that you can buy them. So some countries have more restrictions than others. I think Italy, for example, I think you actually have to provide some proof that you have a business or a home there, like you actually have to have an address there. And some other countries just do not care quite so much whether or not you use one of their domains. And it sort of makes sense, I think, for Tuvalu that they can capitalize on this. And also because, I mean, they're so small that most likely not everybody in that nation is going to be using all of the domains that are possible in existence. Now, in addition to top-level domains, and in addition to sort of the domain as a whole, which we talked about is this, harvard.edu, there can also be subdomains, which are even more specific. So whereas top-level domains are sort of the most generic part of the domain, and then the remainder part of the domain, that's more specific. So harvard.edu is sort of organizational. You can also have subdomains, which within an organization might be used to represent different things. So Harvard, for example, has a variety of subdomains, including DCE, FAS, EECS, Post, Law, so on and so forth, just for all of their various sub-organizations that exist within this domain. And so the domain name system, or the dynamic name system, when it is trying to look up the information for this, basically what happens is that it looks at the domain that you are requesting. For example, fas.harvard.edu, and it will first look at the top-level domain, and there is a hierarchy of DNS servers. The top level of which is responsible for a top-level domain. So there might be a DNS server associated with, for example, .edu. So the very first thing that the domain name server would do is contact this server and say, okay, well, I know that I have a top-level domain in .edu, and what I want to know is what is harvard.edu. And so this then might respond with another IP address of another DNS server that's a little bit more specific. And in this case, it might actually be Harvard's DNS server. So all of these organizations can actually have their own DNS server as well to provide this sort of level of nesting. So Harvard DNS server might have one, and so they say, okay, well now this is where harvard.edu exists. Now we can ask this system where one of these subdomains might actually be, like Post or FAS. And so there's what's important, the important takeaway here is that there's this hierarchy. There's not sort of one authoritative DNS server in existence in the internet. It's very spread out across a variety of DNS servers. And in fact, when we looked at the configuration, the network configuration for my computer, we saw that when I connected to the internet and through DHCP, I received a variety of configuration options, one of which was my IP address, another one was the subnet mask, another was the DNS server. That DNS server might belong to Harvard. It might actually be this one that actually sort of copies a lot of the information, or it doesn't necessarily copy, but at least caches a lot of the information, so that when I ask the server what the IP address of, say, CNN.com might be, it will try to figure that out through this hierarchy of DNS servers and remember that answer for a certain level of time before that record expires, and it will have to go fetch that from that hierarchy of DNS servers. So the important takeaway here is that there's more than just one DNS server that exists on the internet. It's spread out all over the place, and through this hierarchy based on the top-level domain, then the domain, then the subdomain, can we figure out what IP address we are actually trying to go for. Now realize that we can have even further subdomains as well. Generally, you don't see much more hierarchy than this, but it is certainly possible to have more than just one subdomain. You could have a nested subdomain within that as well. Now, any questions on, oh yes?
I've seen occasionally something that's .me.
Right.
What is that?
.me, let's see, so that's definitely a top-level domain, but I don't know offhand if that's actually a country code. Hopefully my little cheat sheet here, oh yeah, it's .me right here is a country code TLD. So if we wanted to find out which country it was, I don't happen to know offhand, then a quick Google search would reveal. So you could just look for ME country code TLD, and probably something like Wikipedia or some other resource would be able to tell you what country it's from.
Something after that?
I'm sorry?
Wouldn't there be something after that indicating if it's an organization or a company or whatever?
Something after that indicating if it's an organization or, oh, so you mean the equivalent of .com?
Yeah,
so
something like blah, blah, blah.co.uk.
So
ones that I've seen is a little bit of you have been a person's name, someone's personal webpage.
right, so for example, the domain that we looked at in traceroute last week, cnn.co.jp, realized that this breaks down in a similar way. There is a .jp for the top-level domain, which is this equivalent of the .me that we're talking about. But usually there's not anything after, or in fact there's never anything after the top-level domain. This is the highest level of the hierarchy. Yeah, but so before, so this .co or this co.jp is actually a domain name. So this is probably owned by some company or by some entity that then gives out subdomains to this co.jp or co.uk domain. And so then this entity, so this body, whoever happens to be responsible for that domain, would then be able to give out a subdomain, whether it's for purchase or not. It's sort of unclear. Probably depends on the entity itself. But then they could then resell or give away these subdomains that belong to this IP. So just because this has something that looks familiar, like a .com in it, or the equivalent of a .com,
What I'm trying to say is that it doesn't. So I'm wondering if this could be something different. That the one or two I've seen were someone's personal webpage that consisted of their name and then .me, the person's personal name.
So
Maybe the mobile me. Do you know mobile me? Apple?
right, so MobileMe is owned by Apple, and they are probably using. So I know that. Let's see. I don't know I know that they own, for example, @me.com, and so that domain is me.com, and that's different. So having a domain name, something like, I don't know, darmend, my username @me.com. That's different than having something that is that's like darmend @dan.me. Right, because the top-level domain in each of these is the very last item. So .com is the top-level domain here. .me is the top-level domain here. .me, in the case of this address, and realize that these addresses translate not only to email addresses, but also web pages and anything that basically has to look up the host name. So this .me is actually a country code, as you can see up here. So this is owned by some country, and it's possible, it might be possible, depending on that country code's policies, whoever runs this country code, that you can, as a person that does not live in this country, be able to purchase a domain that has your name .me. So that's certainly a possibility. And so even though me.com is owned by Apple, this is something that's a little bit separate, just because these are separate domain names, even though they look similar because they both have the word me in them. Yes?
I just looked it up on Wikipedia.
Okay.
I want to know what they say.
What is the ME country code?
Yes, it is the country code. Exceptions to this rule were granted to WordPress, Facebook, GoDaddy, and Yahoo.
So okay, so who owns it? What's the country code for?
It is the country code for Montenegro.
Oh, okay. So according to Wikipedia, .me country code belongs to Montenegro, and so they can actually, it's specific to them, except they provide exceptions for a variety of things. It sounds like some blogs, WordPress, and some other things that would allow you to purchase a domain at their country code. Yes?
I have two quick questions.
Sure.
Are there a set number of top-level domains?
Yes, the top-level domains are fixed. You cannot create one that does not exist here. It has to go through a body that approves all of the top-level domains. And so, in fact, there's been a recent hoopla about creating a new top-level domain for porn sites. And they've been saying, oh, what should the top-level domain be for that, if anything at all? And so they've been going back and forth about that sort of thing. And it's sort of this long thing that's been drawn out just for something awfully specific. Yes?
Is the country related in any way to its IP or location where the server is?
Is the country related in any way to its location or IP? So, well, yes, I mean, so I'm having a hard time answering that question because obviously a country is located somewhere geographically. Oh, the DNS server itself? So not necessarily. So each of these, so it's not necessarily, the domain name servers responsible for each of these top-level domains, they don't necessarily have to exist within the countries themselves. I imagine most of the larger countries would actually host their own DNS servers, but it doesn't have to be the case. Just by the way that the internet works, this is only a mapping to IP addresses, and that separation allows any IP on the internet to be able to use or to be able to be a DNS server if one is set up to be that way. Yes?
So is there like one overarching DNS server for all the top-level domains?
There is no one overarching DNS server for the top-level domains, no.
So how does it check, you put in top-level domain, and it checks that first, right?
So if you enter yes, so when you go to something like harvard.edu, for example, what the basic steps are, your computer asks whatever DNS server is configured on your network configuration, what the IP address of harvard.edu is. If that DNS server happens to have that answer cached, then it will return that immediately. But if not, because say harvard.edu is not a domain that's looked up very frequently, then it will look up the top level, the DNS server that's responsible for that top level domain. So there's a list of DNS servers. There's sort of this authoritative list that maps top level domains to an IP address that's meant to be this authoritative list for each of these top level domains. But it's not the case that there's one big server that hosts all of them. They're probably splintered all over the place, and probably a variety of them host multiple top-level domains as well. Any other questions? Yeah?
So who's the body that actually, are these people that are voted in, or are they, who decides this?
Who decides the top-level domains? I forget offhand. There's some internet governing body. I don't know if they're elected or if they're selected by committee. I don't really know, to be honest. But I believe so. I believe they are international, but I don't know the details about it. I just know that there does exist this body that defines what are allowed country, or what are allowed top-level domains. And in fact, I think just recently they now allowed non-Latin characters. So for example, now top-level domains can include, for example, Chinese lettering and I think also some Arabic. I believe those are the two major ones. They probably have some other ones as well, and that was sort of an interesting update that they did to the top-level domain system, or the top-level domains that exist right now. So there are actually more TLDs than are listed on this slide as well. Okay. So don't forget. So there's in a domain you have something that looks like harvard.edu or cnn.com. Or anything like that. And then, of course, you can have the top-level domain, which is the furthest right aspect of that. And you have the generic top-level domains, com, edu, gov, mil, net, rather, org, and all of the country codes that exist as well. And in addition, there's a variety of new ones as well, like .mobi, that's supposed to represent mobile, .museum, .name. There's just a whole bunch of generic TLDs, not all of which have actually caught on these days. And of course, you can also make it a little bit more specific as well and have a domain that looks like, that includes a subdomain as well. In fact, something that a lot of people tend to do, not a lot, but what some people tend to do is they try to play tricks with the domains that exist, and they try to make words out of the combination of subdomain and domain and country code as well. So for example, there is a service called Delicious, which looks like this. And so this is just this is an actual domain name that includes the DEL subdomain in the ICIO domain and the US country code. But altogether, it actually looks like it's a word. And so this is something that's interesting that some people now try to do quite often, I think, but some of the most useful country codes, like .it, for example, from Italy, a lot of those are actually difficult to obtain a domain from unless you actually happen to be living there. But so just be aware that all of this stuff still takes effect, even if we have something that looks like this, and even if we have a lot of sort of crazy things in front of this. So realize that we could have another domain. In fact, this is something that's sort of relevant to internet security. Let's say that we had something that looked like this. So harvard.edu.badguy.com. harvard.edu.badguy.com. So what is this domain? If I were looking at a website on this domain, harvard.edu.badguy.com, does this mean that I'm on Harvard's website? No, it doesn't, just because that is listed as a subdomain to badguy.com. So this is actually the site that owns this subdomain, Harvard. So harvard.edu in this case is just a subdomain to this full domain here that includes badguy.com. And in fact, you'll see this a lot. You'll see that especially in phishing emails, and we'll talk more about phishing in the security lecture, but in emails that try to obtain your username and password to various sites, even though these sites do not belong to, even though these sites are not who they say they are, they might try to use a trick like this, where you can look at it and say, oh, harvard.edu is in the front part of the URL, so this must mean that it is in fact Harvard's website. And that's just something to watch out for, that they can use tricks like this to change the domain name or to make it look like it's a different domain name than it actually is. Okay. Now, in order for us to start talking a little bit more about some of the nitty-gritty in internet and the networking, we do have to talk about a couple of important relationships. First of all, a lot of the things that we've been talking about follow this model, this sort of client-server model. And this model is very much like when you visit a web page, your computer is the client, and you are requesting a web page from a server. And generally, a server is something that we think of as being this big machine that has a lot of hard drives and is very loud, is very noisy, is very expensive, something like what we see at the very top here. That doesn't necessarily have to be the case. In fact, server really can change meanings depending on the context. So my computer, even though it's just sort of a tiny little laptop, could in fact be a server for a certain number of services. The same thing with my phone. Even though it's just a phone, it can also be a server. It can actually host. It's possible to host web pages. So even though we talk about servers, you really have to think about it in context. What does server in this context actually mean? Now, most of the time, almost all of the time, when we're talking about a client-server relationship, we are actually referring to this, where your client is, or the client is in fact your computer, and the server is some big machine that exists elsewhere on the internet. But there exists also another model as well that's actually relatively popular, and that's peer-to-peer. And so both of these, in effect, act as both clients and servers. Both of these machines are sort of communicating with each other. And so really the idea of a client and server is that with a client is usually requesting data from the server. So the server has a whole bunch of data, whether it be a web page or any variety of information that you want. Like this DNS server has a whole bunch of host mappings from domain name to IP address. There's a variety of other servers as well. FTP server, and we'll talk some more about that. Mail servers, all of this sort of stuff. So all of these things have content that your computer wants. So you are the client requesting content from the server. And so really peer-to-peer then is you sharing content with each other. And peer-to-peer was really much more popular, especially in the days of Napster and Kazaa and all these other file sharing sites, where this model was actually much more popular. But this actually continues to this day with more modern protocols like BitTorrent, and instant messages that actually open a direct connection between one computer and another. In these cases, these are actually peer-to-peer machines. Now, in each of these cases, realize that it's possible for every machine, and especially servers, to operate services on a variety of ports. So what this means is that one machine, one big computer sitting somewhere, can operate a variety of servers. So what I mean by that is that there could be one machine responsible for, say, serving websites. And that same machine could also be responsible for, say, providing email. And it also could be responsible as a DNS server. It could also do file sharing. It could do a whole bunch of things. And so one machine then is, in essence, multiple servers. So this is what I mean, where the context, it really depends on the context of the word server. In this case, we're using the word server to mean it's serving an actual protocol. It's actually serving something that we want to connect to. Whereas we could also call the actual machine itself a server, because it is, in general, a server that's serving up all of this content, that's providing all these things. So again, really don't get confused by the fact that we're using server in a variety of different ways. It's just that it could mean either something like we could be referring to a machine in general, like a generic server machine, or we could be referring to us actually providing a protocol, or us actually providing some service on that machine. Now, in any case, a server can actually provide all of these different services through the use of ports. And each machine can actually have a variety of ports from 0 to I think about 65,536 or so, something like that. And what each of those ports allow you to do is to connect to a server operating on this machine off of that port. So we have a whole bunch of services that we have just been talking about. So for example, HTTP is the sort of protocol that we would use for web pages. FTP is something that was popular, especially a few years ago, for transferring files. POP3, IMAP, these two are both used for email, for example. And so all of these are just the names of different types of protocols or different types of services that a machine can provide. And a machine can't actually provide a service on the same port. That wouldn't make a lot of sense. If I tried to connect to a server that was operating a web server, for example, and on the same port that server was also operating an email server, for example, it wouldn't know what to respond to. It wouldn't know what exactly is going on. And so this is why we have ports, is that it allows us to use multiple services, multiple protocols on one machine without the machine getting necessarily confused. So a variety of these protocols actually operate on known ports. So HTTP, for example, almost always operates off of port 80. Almost always. IMAP and POP3, that actually changes all the time. Sometimes you will see, I think, 25 and sometimes 487 and some other ones as well. But each of these are ports that are sort of commonly used ports for IMAP and POP3. SSH, secure shell, that allows you to create a secure connection between your computer and a server and to issue some commands to it. That usually operates off of port 22. So just all of these things can operate off of these sort of known ports, but nothing is stopping these services from operating off different ports as well. But before we talk more about that, realize that each of these protocols use this concept of clients and servers. So if a server is going to be hosting one of these, if a server is actually going to support this protocol, then that machine has to be running some software on it that acts as a server for one of these protocols. And almost all of the time will this protocol operate off of this port. And so when we're talking about ports, think about it sort of, let's see, so if a server is providing a service. So one of these protocols, for example, like IMAP or HTTP for web pages or FTP to share files, then we can imagine that we want to actually provide each of these services in different places. So an analogy for this might be something like, like a marketplace, for example. So when you actually go to a market or when you go to a mall, you can actually find out each of the stores in that mall is operated out of a different location. And it's the same sort of idea. We wouldn't want all of these stores in one location, like you would have to go in there and it would just be sort of a big mess. But you can look up in the map, for example, you could look up where each of those services are located, and then you can go to that specific location and retrieve that data or that thing that you actually want to purchase. And so this is sort of a weak analogy for what the port actually is as well. So we can operate servers on different ports just to allow our machine to run a variety of different protocols off of it. And so we can then run all of these various things. So there's a whole bunch of other protocols as well. AFP, Apple Filing Protocol, BitTorrent, BootP, DNS, DHCP, IRC. There's secure versions of almost all of these as well. So for example, HTTP is the insecure version of HTTP. It's the insecure way that you would get web pages. That operates off port 80, whereas HTTPS, the secure version, where you would actually connect to, say, a banking website or anything like that, actually operates off of a different port, 443. And so you can actually contact each of these servers dependent on the protocol that actually exists. And so just to give you an idea of what I mean, realize that in almost all cases, can we visit a web page and not only specify, for example, its domain name, but we can also specify its port number as well. So for example, if I wanted to visit computerscience1.net, I can also specify the port number that I want to contact. In this case, in a URL, in almost any time when you can enter in a domain name, you can enter in a colon and then the port number after that. We talked about how HTTP almost always operates off of port 80. And so what's going to happen when I hit enter on my browser is it's going to look almost exactly the same as we've seen before. When I hit enter, we're just going to expect the web page to load. In fact, after a few moments, we see that it does, in fact, load. So what this means is that we have, on whatever machine is hosting this web page, there is a web server operating off of port 80. Yes?
Say HTTPS, what did that be port? Whatever, 440 or whatever that was?
443, uh-huh.
Yeah.
So in this case, yeah, no, so you notice that it went to HTTPS. That's because we actually forward all HTTP connections to HTTPS to be secure. So I can also go to sort of prove this same point, I can go to computerscience1.net, but notice now that the protocol is HTTPS at the very beginning. I can go to 443, and you will see that the same thing results. So I go basically to the same web page. Yes? HTTPS, yes, it is technically a different protocol just because it's the secure version of it. It encrypts the information going both ways, but once you go beyond the encryption, then it's essentially the same protocol. But for all intents and purposes, because it's encrypted, we can consider it to be unique. Any other questions? Now, a lot of times what you might see if you're visiting a website that's sort of hosted by a small company or by or by somebody that's just sort of trying to host their own website, you might actually notice that the URL is not hosted off of the typical port. And so sometimes other ports that you might see are 8080, just as an example. And that's just another port that can exist, that rather a web server can exist for you to contact. Now in this case, if I were to hit return, we're not actually running a web server on port 8080. So what's going to happen is probably it's going to eventually time out, I hope, and it won't actually load up this page. So notice that it's saying it's connecting to computerscience1.net, but now it's connecting to that port specifically, and because there's no server operating off of port 8080 on our server, computerscience1.net, nothing is going to happen. Eventually it's just going to time out. But it is possible to specify that you want a web server to run off of a different port. And this is useful because if you don't actually own the machine that you're running, so for example, let's say that you are running, you are on a shared machine with some other people as well, then chances are you can't actually run a server on ports lower than about 1,000 or so. And so using a very high numbered port like 8080 allows you to circumvent that issue. And also, and you didn't hear it from me, a lot of ISPs actually filter, they actually block servers that are running. So let's say you are sitting at home and you decide, oh, I want to run my own web server. You certainly could do that, but most ISPs actually block incoming connections at low port numbers. And so by running a web server at a high port, you can sometimes get around that same limitation. This isn't something that I recommend just because if they catch you, most ISPs frown upon you running your own web page, you running your own web server, but it is something certainly possible that can happen. Okay, so now you can see that the request is timed out. That's just because it tried to connect to computerscience1.net at port 8080, and no server actually exists on that port at all. And so that's what is allowing this, or that's what brings up this specific thing, this specific problem right here. Now realize that this is relatively low level. When we are talking about ports, we're talking about a pretty low level thing. This is sort of on the same level as nearly as IP addresses. And so when we are asking our computer to contact a DNS server, for example, it's contacting a DNS server and it's doing it off of a specific port. Or when we ask our computer to connect to a web page, even though we usually don't type port 80, it's implied that most of the time, unless we're at HTTPS, are we going to be visiting a web page hosted by that computer on port 80. But the HTTP protocol, all of these protocols actually communicate at an entirely different layer. So all of this stuff that we've been talking about basically implies a different set of layers for all of this data. So at the very low level is this actual physical connection that exists between, say, your computer and your router. So in the case of my computer, I'm not connected using an Ethernet cord, so I'm just using wireless. So this means that the link is basically the wireless waves that exist between my computer and the access point that exists down below. But this same link can actually be a physical connection as well. It can be a satellite connection like we've talked about. And all of these other things build upon these actual links, these actual connections. So the next thing above that would be the internet. So for example, IP addressing. So actually providing an IP address actually exists one level above that, just because we are then using the link to communicate in this world of IP addresses. And IP addresses, all of this stuff communicates in packets, basically. All of the requests that we are issuing, whether it be to a web server, to a DHCP server, to a DNS server, anything, to a mail server, it doesn't really matter what it is. It all boils down to breaking up our request into packets, and our packets are then put into this sort of IP layer and sent off into the world. And at the very top of this hierarchy, and this is a simplified version of these of this TCP/IP model that exists. There's actually 7 or so layers depending on the model that you're looking at. But the very top layer is the application. The application are these protocols that we had just talked about before. So FTP, HTTP, IMAP, POP, SSH, SMTP, all of these other things, DNS, DHCP, all of this rests on top of these lower level things. All of these rely upon, first, the physical link that exists between your computer and the router or the internet at large. And then on top of that, it relies on the IP address and the packets that are broken up at the request of our computer when sending this data from one point to another. And on top of all of this are these protocols. And each of these protocols allow computers to basically just send very simple commands from one to the next. So let's break this down just a little bit. So we've talked about how when I open up my computer and I first connect to the internet, there's a variety of things that happen sort of behind the scenes. The first thing is I actually cause a link to be started, whether that be a Wi-Fi link or whether I am physically connecting an Ethernet cable to my computer. It really depends on my mood and what's appropriate for my computer and the internet connection at my particular location. So let's say that I first accomplished that link by, say, turning on Wi-Fi and connecting to the Harvard Wi-Fi network that exists. Then after that, my computer does not yet have an IP address. It needs an IP address. Recall that all computers on the internet require IP addresses to be able to send data from one place to the next and to retrieve data from a server, for a server more specifically, to send data back to our computer. All computers have to be addressed with this IP address. So my computer uses this protocol called DHCP, which operates at this sort of low level, and it says, okay, I want an IP address. And so there's a DHCP server somewhere that exists somewhere in the network, and it replies not only with an IP address that my computer can use, but it also replies with a variety of other useful things that we talked about last week, like the DNS server, the subnet, and the first router that my computer should use when trying to send a message out to the internet. Now, once all of that is done, then I can start to actually send some data. So for example, I actually want to visit a web page like computerscience1.net or cnn.com. And so when I enter in that information, all of this stuff relies on the sort of the previous layers that exist before it. So let's say that I visit a web page, just as an example. And that web page is sending back some data to me. And that data is just going to be in very simple form, just something like just some text that I'm not quite sure what it is yet, just because the server hasn't sent it to me. Now, what happens at the very low level is that all of that data is broken up into packets. All requests that are sent over the internet are broken up into packets so that they can be sent in relatively small chunks. So I have here actually a demo of what this is going to be like. So pretend that I am a server and somebody here is actually a computer, and you as the computer have requested some information from me. So I've actually received your request, I've processed it, I've determined what sort of data I actually need to respond with, and I've actually created that data on a sheet of paper. And so my message is over here. So now what I'm going to do is I'm actually going to rip up me as the server, and I'm actually going to rip up this information into a variety of packets, and this packet will be sent to the receiving computer in a variety of, in this case, envelopes, which is just an analogy for this packet. So realize that we have a response, and this response can be big, but this response is sent to us in quantized packets, in relatively small packets. And all of these, whether it be a big message or whether it be a small message, it's always sent to us in these packets. So I'm going to need a volunteer, somebody who doesn't mind giving me either their real name or their fake name. Nobody. Yeah. Well, so you can stay there. You don't have to come up here or anything. I just need to know either your name or a fake name. Just Jonathan. Okay. So what I'm doing now is I'm actually I'm addressing these packets. And so in this case, I'm pretending that the name Jonathan is actually an IP address. And so what I'm doing then is I'm actually creating a series of packets with the response, with the request, or with the data rather, that I want to send to Jonathan. And so a packet is actually a pretty complicated thing. There's a lot of little bits and pieces of information associated with it. Don't worry about all of this junk. Basically, realize that packets include just the basic level of information, including who this is to. So in this case, this series of packets is to Jonathan. And it also includes who it's from. So in this case, it's from Dan. And also, another thing that it includes are numbers, the numbers of the packets. So in this case, you'll notice that I have 3 packets here, and they're numbered sequentially. This is packet 1 of 3. There's packet 2 of 3, and there's packet 3 of 3. So now I have broken down this request, or this response rather, into a variety of these small packets that I can now send over the internet. And so basically what's going to happen is I'm going to just pass it along to my router. Rose, can you be my router real quick? So basically I'm going to pass these along to my router, and my router will decide what is the best route to send these packets. So basically all you need to do is just pass them along, and preferably you will decide that you will pass one along and decide that route is no longer good, so just sort of distribute the 3 packets everywhere. And so basically, what should happen is that these packets, they're being passed from router to router. Each router is looking to the destination of this packet. And then that router should then decide to pass it along to the next destination that will be closer then to ultimately Jonathan. So this is essentially what we've been talking about yesterday, or not yesterday, 2 weeks ago, where what we wanted to do was break down, send these requests over the internet from router to router to router. Each of these are hops. So all of you that are participating in this are actually a hop in this larger internet. Okay, so would you mind, would you mind actually tearing up the packet? So just tear it up. So you are a bad router, and you have decided that you don't like this destination or this packet, so you've actually torn it up. Okay, so that's good. So let's continue. Continue passing along all of the packets. It doesn't matter, right? No, you don't have to pass along the torn up packet. So just for some reason, let's say that router doesn't actually have a connection anymore. Let's say that router has become dead for whatever reason. Through any variety of means, a packet can be lost at some point. Just like we have lost one here. We don't know which one quite yet, but that is why we have actually numbered each of these packets. By the time Jonathan actually receives all of these packets, and you'll notice that we have here a little bit of latency, and this is one of the reasons why things also are a little bit slow on the internet, because they can actually be taking perhaps different paths from one router to the next. It could actually be taking us a little bit of time to pass all of our packets along from one computer to the next. But ultimately, Jonathan will receive all of the packets, and he can look at them and say, okay, these are to me, and they are numbered. And on these numbers, I can see that I have, say, 2 of the 3 of them. And Jonathan, which one are you missing? 3. So basically he responds to me, and he says, okay, I received all packets but number 3 of 3. And so me, being the computer that initiated the request, can say, okay, well, that's fine, that's no big deal. What I can do is actually recreate that packet. And so I didn't know then what packet was going to be lost, so I have to recreate the message that's in this packet, put it back in here, and then renumber the packet. This is packet 3 of 3, and again, I have to re-address it to Jonathan. So this is to Jonathan from Dan, number 3 of 3. Pass it back to my router. And then my router will pass it back to Jonathan. And basically, what's going to happen is that now, even though this message has been broken down, and even though the perils of the internet have caused some of the message to be lost, now what you can do, Jonathan, is actually open up all the packets and reconstruct the original message based on their numbering so that they're ordered from 1 to 3, and so we can just then recreate this data that I have sent to Jonathan. And so basically what he will do is then just open all of the packets and retrieve the data from these packets and reconstruct them based in the original order that I had sent them in, because they were, remember, numbered and ordered. And so then I know then what the message is. So Jonathan, what is the message?
Oh, hello.
Oh, hello.
Welcome to the net.
Welcome to the net. So that is the message that has been broken apart into basically 2 words per packet. That is the message that has been sent to Jonathan. And so using this is how the internet actually works at a sort of low level, where we can actually relatively low level, where we can actually, even though this message to Jonathan was in English, I used this idea of IP packets to send that message along. So this message was broken down into packets addressed with a to address, which even though right now was a name, but in the concept of the internet would actually be an IP address. It also had a from address so that everybody knows where this message came from as well. And all of these packets were numbered so that in the end, it doesn't matter what order the packets arrive, they can be reconstructed in their original order and the original message can actually be received. Yes?
What part of the protocol defines how or like at what point the client says to the server, I didn't receive the packet?
At what point does the client tell the server, or vice versa, that I have not received the packet? This is very low level. This exists down in the sort of IP level here in this set of layers, where it's basically all of this stuff is performed by your network card. So whether it be an Ethernet card or by your Wi-Fi card, all of these packets are received, and there's a certain timeout that exists. There's a certain amount of time that a card will wait for all of the packets that it expects. If one has not been received in that time, then it will respond to that initiating server and say, okay, I'm missing packet N of 15 or what have you, and it will actually then get resent over the internet until all of the packets have been received. So this is a pretty low level thing. Most of the time you're never going to see any of this stuff. You're never going to know what order packets come in, but this is important to realize that your request, and it doesn't matter what sort of request it is, whether it be to a web page, whether it be to an email server, whether it be to a file transfer protocol, all of this stuff is broken down into these small packets and sent over the internet from one router to the next in this manner. Yes?
If the name is entered on 2 different computers with 2 different IP addresses, is it kind of the same general packet breakdown, or is it totally random and varies?
I'm not quite sure what you mean. If there's 2 different servers if 2 different computers that go to the same domain?
Is it always broken out the same way based on the same request, or is it different?
No, the requests, the data is not broken up in the same way. It really depends on what the contents of that data are. So I suppose if you are responding with the same data over and over and over again, then sure, those packets will probably look the same because that data has not changed, and there's probably not much randomness in terms of packing one of these packets. And in fact, the packets have a very well-defined size where they can maximally be so large. And so they will fill up a packet up to that much and then move on to the next packet and fill up that packet. So I suppose it's possible that, or it seems probable, in fact, that if you are sending the same data over and over and over again, then it's sort of the same packets over and over and over again. But what will be different then are the to address mostly the to address. They'll be just addressed to different IPs on the internet. Any other questions? Okay. So with all of that said, realize that now things like HTTP, these are actually protocols, and these can actually, the way that this works is a much higher level. It's much higher up this chain of layers. But realize that all of this stuff that we talk about in terms of protocols is then broken down into these packets. Whether it's a DNS request, whether it's an HTTP request, it's still broken down into packets and sent to the appropriate IP address. But when we talk about protocols, an actual application like an email or a web page, then there's a separate concept related to protocols altogether. For example, if we hijack the HTTP headers, as it's called, we can actually see the actual protocol between my computer and a server when I'm looking at a web page. So, for example, when I go to https computerscience1.net / and then a whole bunch of other stuff at the end, my computer actually has to initiate a request from my computer to the server. So first of all, how does it know what server it is? Well, okay, let me rephrase that question. What is the server in this top request that's highlighted right now? Right, computerscience1.net, but more specifically, it's www.computerscience1.net. So www is usually a subdomain that most web pages actually operate off of. Doesn't really matter if that www is there. In the case of our computer, in the case of our server, we actually forward requests that come in for computerscience1.net only. We forward them over to www.computerscience1.net. That's sort of an uninteresting, or rather a not really necessary implementation detail. So okay, so my computer knows that it has to contact www.computerscience1.net. In fact, that's the host thing that you see here. Now, this text that you see after that sort of space in my request, this is the request that my computer sends to that server. My computer looks up the IP address of www.computerscience1.net. It then has the IP address of that server. Then it connects to that server on what port? Because this is HTTP. Port 80, right? So it connects to computerscience1.net, rather www.computerscience1.net on port 80. Then a connection is established. And remember, all of this stuff that's happening is happening over packets. But we don't care about that. That's at a much lower level than what we're looking at right now. Then I begin my request. This very top line, get / 2011 / spring / main _ page http / 1.1. Now this request actually specifies to the server a variety of things. First of all, you can see that I'm trying to get a web page. I'm trying to get the contents of a web page. Next, the very next thing that you see is the page that I want on this server. In this case, it's / 2011 / spring / main page. Right? And you can see that that's part of the request at the very top, just without the server, because we're already connected to that server. We don't have to specify that. Next, after that, we see that it says HTTP / 1.1. This is the protocol that my computer is actually using to communicate with this server. We are actually using the HTTP 1.1 protocol. We're telling that to the server, so the server knows, okay, if I support HTTP 1.1, which it does, then I will respond in the HTTP 1.1, version 1.1 protocol. Now, my request that isn't actually done. I can actually send a variety of other things as well. For example, host, I'm telling it, and this may seem redundant to tell the server that I'm connected to what server I want to get the data from, but this is actually important because we talked about how multiple web pages, multiple domains can actually point to the same IP address. And so if one computer is a web server, then how does that computer know which domain you are actually requesting? It's using this request right here. So I'm actually telling this server, okay, you might be hosting a whole bunch of other web pages, but I want main page from computerscience1.net. Now my request continues. I give it some information about my computer, and this all happens under the hood in your web browser. The next line is the user agent, and the user agent just tells us a variety of things like, you'll see what kind of computer I'm running, what version it is. It's a Macintosh running Mac OS 10.6. It's an Intel Mac. And in fact, if I scroll over to the right a little bit, you will see that it even tells you what version of a browser I'm using. I'm using Firefox 3.6.13. It also tells you what my language is, English US, EN-US, and sort of the left over here. So in the user agent string, the browser tells the server a variety of information about my computer. Now, some of the other stuff isn't that interesting, so we'll skip over this, but all of this is still part of the request from my computer to the server. Yes?
How much of this was in the original internet, and how much of this is additions to solve problems that arose, and what were they?
How much of this existed early on in the internet, and how much of this now is relatively new? So I would say,
Were you specifying language, or
I'm sorry,
Like,
specifying language?
When the internet started as, local Usenets and
Yeah, so I think when,
in the universities, were you specifying English for the web page?
well, this protocol is this text that you see here is specific to the HTTP protocol. But I suspect that all of this stuff, all of this actually, a good number of this is actually optional, and this depends on what the server will accept. So you will notice that all of these are in the form, from here on down, it's in the form some word, and then a colon, and then data after that. So these are this is called HTTP headers. So this is information that my computer is sending to the server, and nowadays modern browsers send almost all of this information. I think initially we didn't see very much, if any, of this information except for this sort of thing, the actual web page that we wanted. It really is up to the browser and also the server what is sent back and forth. So in this case, my browser has decided to send all of this information to the server. Now this is my request to the server. And now the server says, okay, processes all of this information. It says, okay, it decides what it wants to do, and it sends headers back to me. And these headers are actually sent right before the web page is sent. So this is the response from the server. HTTP/1.1, again, that's the protocol, 200 OK. So 200 may not look very common, and that's actually, but it's sort of a white lie, because 200 is actually the most common HTTP response that you will get from a server, just because that means that everything is okay. But you have probably seen other ones as well, like 404 or 400 or 403 or 500. This is the code that is referring to. And this is the code that's returned from the server. If you see like HTTP error 404, something like that, file not found, that is an actual HTTP error code that says that my request, my GET request, cannot be processed because this file that I've requested just does not exist. It's not found for some reason. There's a whole bunch of these error codes as well. 403 means permission denied, and there's a whole bunch of other stuff as well. But most of the time, you don't see these codes, but the most common one is 200, just because you're indicating that, okay, that file has been found, and I can return it to you. Now you'll notice there's a variety of information that the server sends to my computer as well, like the date, the language of the content, what sort of server it actually is. Apache is actually the name of a web server, a very popular web server that exists. It's just you can download it, you can actually run an Apache web server on your own computer. You'll notice a variety of other things that relate to the data as well. And so this is this is the behind the scenes, the protocol, the HTTP protocol that's sent from my computer to the server, and this is the response from the server back to my computer. And remember that all of this stuff, even though this is all text, this is still being broken down into packets and being sent over the internet in that small packet form, in these small envelopes, so to speak, and then it's rebuilt by the receiving computer, and any packets that were dropped are invisibly requested back from the initiating computer and sent back, so that we basically get this in the end. And actually, it's completely possible to, and hopefully I'm not going to mess this up, even though it's very easy to mess up live demos here. You can actually communicate with the server directly in HTTP. So for example, you can open a connection using Telnet to www.computerscience1.net on port 80. What will happen is that it says, okay, I've performed a DNS lookup, and I've found that www.computerscience1.net is found at 140.247.63.234. And so now I'm actually connected to port 80. So what I can do is I can actually type a request, get/http/1.1. Now what get/ means that I just want, if you were to type a page, if you were to type a domain like cnn.com and not type anything after that, that's what it's referring to. It's just the default, it's just the blank, the default thing that we are requesting from them. And so what this means is that when I hit enter, it's going to return to me, let's see, after this, it's going to return to me what is going on. And so you can see I've got an error code, http/1.1 from the server, 400 bad requests. And it gives me, again, the headers. But you can see that down here, there's actually a web page. And it says that you can sort of, there's a whole bunch of gobbledygook, but you can see that it basically says your browser sent a request that this server cannot understand. So let's retry this request, but instead let's do something that is more compliant with the spec. So in this case, I'm going to do get / and then http/1.1. Then I need to specify the host, www.computerscience1.net. I hit enter, and then the way that the server knows that I'm done with my request is that I put in a blank space. Now you can see there's another response from the server. And even though I've retrieved or I've requested the default page, the one at /, normally keep in mind that the default page that you would find is something like index.html or index.http, or not .http, .php or .htm. All of these are sort of the standard default, but we are using some non-standard default page just because we're using MediaWiki. And you can see that what it's returning to me is moved permanently, and there is a different location. It's been moved to some other location. And so I can actually then, if I were to send this, I should probably use a different host than I will after the break. But we can actually get the actual document that's been requested by my browser. So let's take a quick 5-minute break, and when we come back, we will keep talking about the internet. Hi, everybody. So before the break, we were talking about the HTTP protocol and how this is built upon everything that's sort of below it. Realize that even on top of this protocol, there's data that's sent to us. And we saw all of this data in the form of this sort of like gobbledygook that we saw that's actually HTML. So HTML is this file type. It's just a text file, basically, that includes a bunch of tags that look like this. And it basically just specifies the content and the layout of a web page. And so this is then built even on top of HTTP, where the browser and the server use HTTP to communicate, to figure out which web page we actually want. But when the web page is sent to us from the server, it's sent to us over HTTP, and of course all of the underlying technologies below it, including IPs and packets and all of that stuff, but it's sent to us in this HTML or XHTML, they're sort of interchangeable for our purposes, in this sort of format that's right here. Just to show you then the end result, if we were to go to, say, harvard.edu, we would see a page that looks like this. So there's a whole bunch of stuff here. There's text, there's graphics, there's colors, there's all sorts of funny stuff. But if we were to actually look underneath the hood, we could look at the source code for this page. This page is made up of just text. And it does refer in text to images that the browser can download and display to you. But all of these colors and this layout and all of the text that actually appears is because of this sort of, right now, confusing looking HTML or XHTML web page. And so when I sent a request to harvard.edu, because I'm already connected, what happened was what's the first step in this sort of lookup? When I want to request a web page from harvard.edu, what's the very first thing my computer has to do? Assuming I'm already connected to the internet, I already have an IP address, all that stuff, so I go to harvard.edu, what does my computer need to do?
Get /
So almost, so before that it has to connect to the server, but how does it know it has to do something with the domain? Right, so it does a DNS lookup first. So it doesn't convert. It looks up what harvard.edu should be in terms of an IP address. Then it connects to whatever that IP address is, 140.247.something.something, at port 80. And then it does that GET request, initiating this sort of HTTP protocol. Then after this GET request is completed, the server then sends back to us a text file that looks like this. And my browser then takes this text file, this HTML, XHTML file, and it actually renders it. It displays it on the screen dependent on the rules that exist when laying out a page like this. And this is actually what you will be working on for your final project. You'll actually be creating an HTML page. You're not going to have to worry about all of the underlying technologies. You're not going to have to run your own server. You're not going to have to do anything like that. But what you will be doing is creating this text file that will be then sent from the server to the client and interpreted by your browser to be displayed here on the web browser. So I talked before about how we can sort of fake a communication with the web browser by using this sort of telnet application. So I want to do that again, but show you that because now there's no sort of weirdness going on with MediaWiki, which is the software we use in computerscience1.net, I can actually request then get slash using http/1.1 from this server. What didn't you like? Get slash http/1.1 host www.harvard.edu. When I hit enter twice, then you'll see after a short delay, because the server has to process all of this information, does it send all of this document basically to my computer. And so if I scroll up a bit, I think I've scrolled up too much, we can actually see also the headers that the server has sent back to my computer as well. Hopefully that's going to come up soon. You can see this is kind of a big page. Okay, so this was my initial request, get HTTP, or rather get slash HTTP 1.1. That was my initial request. Then the response from the server is immediately below it. HTTP/1.1 200 OK. Then it also sends a variety of headers telling me some information about the server and about the page that it's sending me as well. So in this case, it's using an Apache server. Again, like I mentioned, Apache is a very popular web server that exists right there. X powered by PHP. PHP is just the language that's used on the server to generate web pages. We're not going to you don't have to worry about that. There's also this idea of cookies, and we'll talk more about what cookies are in the security lecture, but basically a cookie is just something that the server can ask your computer to set. It will just remember this information for a little while. So set cookie platform equals computer, set cookie page type equals basic. So these are cookies. This is some information that the server is requesting that my web browser actually save. Because I'm not actually using a web browser, obviously my computer's not going to save this. We're just looking at this right now. Then we can see some other information here as well. And below that does the actual HTTP page begin itself. So you can see that the beginning part says doc type HTML. This is exactly what we saw in the source code as well at the very top up here, even though Firefox is now making it pretty and coloring it for us so that we can actually see what it is. So this is the exact same thing. So that's sort of a behind the scenes of how this HTTP thing works. And so this is an application that is built upon all of these previous technologies that we have, in fact, talked about. So when we are talking about now sending all of this data from one computer to the next, we've talked about a variety of things. And this is worth repeating because it's important. Every year I see people get confused between all of these acronyms. Remember that you don't have to know necessarily what the acronyms stand for, just what they do, what they mean in the grander scope of things. So we talked about DNS. What does DNS do, basically? And that's not this slide, but what does DNS do? DNS. Basically the phone book, right. So we can look up the IP address given a domain name, or given a specific domain name. We will get returned back to us the IP address for a machine. DHCP, even though they both start with D, they do something very different. DHCP, what this allows us to do is actually perform a request, like I need an IP address, and a DHCP server will then send back to us the IP address that we should use, I don't know, all that other information, the DNS servers to use, the subnet mask, the router, so on and so forth. Then, of course, we have on top of that, we have these IP packets. These IP packets are the data that's actually sent by being broken down. All this data is broken down into these packets and sent over the wire from one computer to the next. And when data is sent from one computer to the next, there's actually a couple of different ways that it can be sent from one to the next. And so there's two basic types of technology, a hub and a switch. And so basically what they do is they allow us to send data from one computer to another computer. So for example, let's say we have 4 computers. One is computer A, then computer B, C, and D. And each of these are connected to a switch through, say, an Ethernet cord, for example. And so a hub and a switch are basically the same thing. What happens is that you being computer A will want to send some data, and this data will of course be broken down into packets, and these packets will be sent from computer A to the hub, in this case into the switch, and each of these devices is responsible for sending this data out to the computers that are directly connected to it. This is different from a router in that a router will send information from one router to the next in order to send data from one network to another network. This one is meant, hubs and switches are meant to be very local. So they're what you are directly connected to. So a hub, for example, is a very stupid device, and it will just send out everything that it receives to all of the machines that are connected to it. And this is not a very smart thing for a hub to do, just because then if I send a request to a machine, specifically machine D, then all of the other machines, machines B and C, will also see. They could potentially look at the packets that I have sent out, just because those packets were also sent to these machines as well. Whereas a switch is nowadays much more common. When you have a home router, for example, that has a variety of Ethernet ports in the back, this usually acts as a switch where it's actually smart enough to know what is connected to it. And it will say, okay, well, I am sending a message from A to D, so I receive a message from A. The switch knows then to send that message to D instead. And so what happens is, what if you have a variety of machines that are trying to send data at the same time? So this is a busy network, for example. You're trying to send data from both A and B to, say, C and D, respectively. So what happens is that this hub then tries to send out both of these things at the same time, but what you get is a collision. It can't actually do this, right? If it gets two packets at the same time, it just is not going to be able to handle it. And so there's sort of this delay that the hub tells the computer. It says, okay, I can't deal with this packet right now. Come back at a later time, and I'll try to send it again. So the computer will wait a couple of nanomilliseconds and then send that packet again. Whereas a switch will actually be able to handle, using separate pathways, it will actually be able to handle this sort of thing. Now, why do I mention hubs if they are old technology, if we don't actually see them anymore? Well, the analogy of a hub, even though we were talking, at least in this case, about wired computers, this extends very well to the concept of access points. Access points are, they exist over the air, and all of the data that's sent from my computer to the access point and from the access point to my computer is just sent out to the air for any computer to potentially be able to receive. And in fact, this is something, it is actually possible, even though most of the time your network card is configured to ignore packets that are not addressed to it. You can actually reconfigure your network card to accept all packets. And as a result, you can actually inspect all of the other things that people are doing. You can see all of the packets that are flowing in the air from all of the computers and all of your cell phones that are connected to the Wi-Fi right now. It's actually possible for another computer to be in so-called promiscuous mode. And yes, that's actually what it's called. And in promiscuous mode, what it will do is it will just read all of the packets. And it will try to reconstruct all of the messages. And so it is therefore possible, using an access point, because in the same sense as a hub sends out all of this data to all of the machines, it's then possible to look at the data that is being sent from one computer to the next. And this is something that you should actually be concerned about, especially if you are on a public network, just because your data can potentially be sent unencrypted. Now, if we were to talk about some of the specifics to the hardware, realize that access points, they come in a couple of different speeds. Usually they're referred to by 802.11 and then some letter indicating the speed. And usually the first one was B. That was relatively pokey at 11 megabits per second. G was faster at 54 megabits per second, and those were sort of compatible with each other. You could actually run an 802.11b network on an 802.11b computer on a G network, and vice versa. Then there's a couple of other ones as well. A, which operates on a different frequency altogether, and it's actually pretty fast. And the most recent one is N, which is 248 megabits per second. Typically you get about 70, and this is a big increase over our B speeds of 11 megabits per second. So just to reiterate, we have B at 11 megabits per second, G at 54, N at 248, and A, which is not really, you don't really see that all too much, but it's typically around 23 or 54, or rather 54 megabytes or so for A. Now, similarly, when we're talking about dealing with these dealing with hubs and switches, usually they're directly connected. And with direct connection, you usually see the speeds in terms of base T. So 10 base T, for example, refers to 10 megabits per second. You might also see 100 megabits per second or even a gigabit, 1,000 megabits per second. And so even nowadays, can you get very, very fast speeds, much faster using a direct connection, especially with a switch and a hub that support speeds that are that fast, and assuming also that your computer can support those speeds as well, much faster than what you can get over an access point as well. So we've talked about what a router is. A router it routes traffic from one network to the next. So it's sort of like it's almost like a switch, but it has a much grander scale. It's on a much grander scale because it knows where to direct traffic, to direct it from one network to the next network. So we've said that, for example, if we want to send a packet from A out to the internet, then the router knows to send that packet out to the internet as well. Now, similarly, if we were to add some IP addresses, and we've talked quite a bit about this last week, about the subnet mask and how the routers then know what is local, what machines are local to that network and what machines are considered to be outside of that network, just by looking at the IP addresses of the machines connected to it and by using the subnet mask, can the router then make a decision? Okay, I'm trying to send a packet to an IP address of like 24.128.128.32, for example. And then the router knows, okay, that is outside of the subnet, which means that it's outside of this network. So what I'm going to do is direct that packet to the other routers as well. So basically, we have a few different technologies. A switch is basically something that's very local. It just is for a couple of directly connected computers to a central switch. An access point is something that allows us to connect multiple machines using Wi-Fi to a wired connection, and an access point is basically it's the equivalent of a hub, but wireless, in that same analogy that we talked about before. And then a router actually directs the traffic from one network to the next. Now, we've talked before, and I did a whole bunch of hand waving about, oh, we're running out of IP addresses, but we're probably not really at risk quite yet. And the reason that this is true is through this technology called network address translation. And how I mentioned before how a router or how a device, a network address translation device, can actually have multiple IP addresses. It can have a public IP address that it displays to the internet at large, and it can have a private IP address that is used to give other IP addresses within the local internet. So we have here, it basically acts like a bridge between our local private internet and the larger, or not, our local private network rather, and the larger internet as a whole. And that's what this diagram is supposed to show. At the bottom is our sort of private network that we have. We have a couple of machines. We have one client that has an IP address of 192.168.0.2, for example. Then you'll notice that there is actually an internal IP address for the router, 192.168.0.1. So all requests that my computer sends as the client out to the internet over to the server at 64.236.16.20 has to go through my router first. And through this, it's not really magic, but through the magic, quote unquote, of network address translation, my packet is first sent from my IP address, from my computer, to this router. Then realize that these IP addresses, 192.168, they're private IP addresses. They cannot be referenced from outside the internet, from the internet as a whole. They're just not going to be addressable by any sense. But my router actually has an IP address that belongs to the public, or that doesn't belong to, but it has an IP address that is addressable by the internet at large. So what this router does is it takes this packet that initially had a from field, that initially looked like it was from 192.168.0.2, and it changes it to say, okay, now it's actually from 24.28.4.43. So what this is doing is that it's translating the addresses from inside to outside. So then now, because it actually has this valid IP address, it can then send the packet to this other server that exists on the internet, 64.236.16.20. And what it looks like to this server is that the request came from the router at 24.28.4.43. So what this means is that when the server replies, it's going to reply to the router, and it's up to the router. The router will then have to figure out, and I'm using router in a general sense here. Router in this case means a home router that includes this network address translation. A general router that you would find on the internet may not actually have this sort of network address translation capability, but realize that this does exist in home routers. So it receives then a packet from 64.236.16.20 and it says, okay, recently did this computer on my network send out a packet to that server, so it seems in all likelihood that this packet that I got back from the server is then destined for this machine. So then it rewrites all of the necessary information and sends the data back to the client. So in this way, can we have multiple machines? We can actually have another client as well, 192.168.0.3 and 0.4 and 0.5, and all of these then share, in a sense, this one IP address that our router has publicly facing to the rest of the internet. And so this then allows us to extend, in a sense, the IP version 4 space, just because then we can have multiple machines, and this router is smart enough to know where to send all of these requests, all of the data that's destined for it. It knows to send it to computer A or computer B or computer C, dependent on the initial requests that these computers had sent out to begin with. And so using then, again, this is network address translation, and using this, it allows us to extend the IP version 4 space just by allowing multiple computers or multiple machines that use IP addresses to share one publicly accessible IP address. Any questions on that? It's sort of an important concept, I think. Okay. Now, another concept altogether is this use of VPN, or virtual private networking. And VPN essentially creates a secure tunnel between your computer and another computer on a different network altogether. The end result being that it looks as though to both your computer and to the outside world that you are on some other network altogether. And so what happens, you can actually use a VPN client, and Harvard actually has a VPN service. You can download a VPN client and create a tunnel between your computer and Harvard, and what you get as a result is this secure connection where all of the data is secure between your computer and Harvard's VPN server. This is actually a very useful thing, by the way, when I talked about before about how all of the data sent between your computer on a Wi-Fi network to the access point is actually potentially exposed. This is a way that you can protect yourself by using a VPN connection, just because all of this data is safe. It's encrypted between your computer and Harvard servers. Now, once it reaches Harvard servers, or once it reaches the VPN server more generally, what happens is that data is then decrypted, and then it's at risk again of being sniffed by people that are on the same network. But the chance of that is perhaps much lower than, say, you being at a coffee shop and somebody else just sniffing all of the packets that exist in the coffee shop. Just because those packets from between your computer and the VPN server are encrypted, you have greatly increased your security. You're not completely safe, but you have at least increased the security of your data. Yes?
If you have someone, say, sitting in a coffee shop sniffing out all the packets
Mm-hmm.
you mentioned, what kind of things, like what kind of information would they have access to? Just like the websites you're visiting, your keystrokes, or what is
The information that, if somebody is sniffing your packets, the information that they would have access to is anything that is not encrypted that's sent between your computer and another computer.
like passwords?
Potentially passwords if they are sent unencrypted. If you go to a web page and it's not using HTTPS, then that data is sent in the clear, as it's called. It's not encrypted, and that data can actually be sniffed. Another thing, it's actually possible to hijack, to do this attack called hijack sessions. So let's say that you are already logged in, and in this case, they don't even have to know your password, but they can see that you are logged into, say, Facebook or to some other website like that, Gmail, for example. And they can actually do something called a session hijack, where because they're able to see all of the information that's being sent between your computer and the server, they can actually then pretend to be you and then take over your logged in session to Facebook and to Gmail. Now, there is a way to protect yourself. That one of these ways is to use VPN, because you're then creating a secure connection between your computer and the network that you are connecting to. But also, if you use HTTPS, most all of these concerns go away as well, just for whatever pages you are on HTTPS. But there was a tool that came out recently called Firesheep. I don't think I have it on this machine. But basically, this tool called Firesheep didn't make it possible. It didn't show, it didn't initiate all of these problems. It didn't show that all of these problems actually existed. It just made it much easier to show that these problems actually existed. And using this plugin called Firesheep, you can actually sit in a coffee shop and you activate Firesheep, and it actually shows you everybody that's logged in the coffee shop to Facebook or to Gmail or to what have you, and you can actually log in as that person. It's actually kind of scary in a way, just because anybody that's using their computer and they're connected to a server in an insecure manner, it's very possible for somebody else to hijack that data and either become you or at least inspect all of the data that's being sent between your computer and the server.
So in that instance, how would you protect yourself?
So again, there's there's two major ways that you can protect yourself. One is to use HTTPS everywhere that you can. Facebook and Gmail now both have options that allow you to encrypt all web pages. So in the settings of both of these pages, can you actually make HTTPS enabled everywhere? So that means that you're then protecting your session from being hijacked from somebody else. What might be a little bit more secure, because those then, using HTTPS is only secure for whatever page you're actually connected to at that moment. Using something more general like VPN, which encrypts all of the traffic, everything between your computer and the outside internet, this is generally a safer option to use VPN, because then if there are any web pages that don't support HTTPS everywhere, then it reduces that problem as well.
How do you use VPN?
So how do you use VPN? So that is a good question. Tying us back to our discussion here. So basically, you are a computer on the internet somewhere, and you have an IP address. So let's say that I am this computer on a network 192.168.0.4, and I actually want to connect. No, it's actually the other way around. Let's say I'm somewhere on the internet. It doesn't matter what my IP address is, and I want to create a secure connection. So I download a VPN client, and you can do this from FAS's download page, and depending on your work also, you might have a VPN connection available to you. But what you do is you establish a VPN connection between your computer and a machine that exists on another network, let's say Harvard's network. What this does is it encrypts all of the traffic between your computer and this other machine, this VPN server. Then the VPN server then retrieves all of that information, decrypts it, and then issues all of those requests on your behalf. So basically, in essence, what it appears is that your machine actually has an IP address on this other network. So for example, even though my client could be somewhere else entirely, I could actually retrieve this 192.168.0.4 address. Or sitting in a coffee shop, for example, and I connect via VPN to Harvard, I could actually get a 140.247 address. And so it appears as though I am on Harvard's network, not only to my computer, but also to other computers as well, because then I basically have that IP address from this other network. So it does a couple of things. First of all, it secures all of the data that's being sent between your computer and the server somewhere on this network. And then the other thing that it does is it makes your computer have an IP address on this other network as well, so that you can access local resources on that network, or you can make it appear as though your requests are coming from that computer or from that network itself, which is actually a pretty useful and interesting thing. Now, realize that there's another type of thing that we can use to protect ourselves. In fact, most computers have these enabled by default, called a firewall. A firewall, all it basically does is it prevents other computers from contacting ports on your computer. So let's say that you have a couple of services running on your machine, and you may not even realize it, just because a number of computers actually have some services like Windows file sharing enabled by default, especially older Windows machines. A firewall will actually prevent other computers from connecting to your computer at specific ports. And in fact, this is a very good way of securing servers as well. You can create a firewall to block all ports except whatever services happen to be available. So let's say it's a web server only. You could block all ports except port 80, just as an example. So then any requests that come into other ports will be ignored or just dropped altogether. Now realize that we're talking about a whole bunch of different devices, but when we refer to home routers actually include a wide variety of services. Not only are they routers in the sense that they will pass information from your internal network to the outside world, to the next router as well, but they are also DHCP servers. They're also switches. They're also access points because you can connect to them using Wi-Fi. They are also, sometimes they'll be DNS servers, but not usually. So DHCP, so that your computer will actually be able to retrieve an IP address from the home router as well. Other things include firewalls, so that it blocks all all port access to your computers, and also network address translation. So all of these technologies are rolled into what we know as home routers. It includes all of these technologies to give us, in the end, the effect that we desire. And that effect is to have, when we open up our computer, we connect, say, via Wi-Fi to the access point, which is this home router. Then via DHCP, there's a DHCP server that each of these routers have. And so then they will assign our computer an IP address and a DNS server as well. And because these routers use NAT, use network address translation, this IP address won't be an IP address from the outside world, but it will be a private IP address. And the routers will then be very smart about converting from or translating from the public IP address to the private IP address that they have given you as well. And so if you have multiple machines connected to it via an Ethernet, via actual cabling, then it also acts as a switch between all of these machines as well. So home routers do a whole bunch of things. They're not simple devices. They're actually pretty complex in that they can support all of these technologies and all of these services as well. Now, finally, one of the last things that's important to talk about is our actual pipe, is our connection to the computer, our connection between our computer and the internet as a whole. And we talked a little bit about ISPs. An ISP is just an internet service provider. And ISPs can really vary in terms of their quality and also how fast of a connection they can give you between the outside world and your computer itself. And so how many of you remember these CDs that AOL would actually pass out? So yeah, so these have become coasters for a great many of us back in the 90s. But basically, AOL was just an ISP. It was an internet service provider where you would use a dial-up connection. You would initiate a link to the internet using a dial-up connection, whereas nowadays, typically what you would find are DSL or cable connections from your home router to the ISP. And additionally, we might also find other ISPs in mobile devices as well, like AT&T and Verizon both allow internet access on their phones, and so they are in essence ISPs because they provide internet to your phones over the airwaves, over these 3G connections. And those are, like we mentioned before, a little bit slower, even though generally what's slow about them is their latency. They have very, very high latency. So recall the difference between latency and speed is that latency is the delay that it takes between my request to be sent from my computer and the response to be received from the server. Generally, the latency on the mobile devices is very, very high. Even if once the connection has been established, it's relatively fast. It's of course not the fastest thing in the world, but once the connection has been established, it's also generally relatively quick. So one of the things that I think is useful to remember from all of this are the different layers that the internet actually exists in, and think about what happens when we actually sit down and we open our computer. When we open our computer, what we want to happen as we connect to the internet and actually visit a web page. But until next week when we have our first exam, oh yeah, don't forget, next week, I didn't say this on camera, next week is our first exam. It is actually cumulative. It includes all of the material up through and including this lecture. And it is going to be, we're also going to have a review session this Friday from 5:30 to 7:30 in Emerson 108, is that right? And then that will also be filmed and placed online. And the exam is 1 week from today and will be I believe, the duration of the class time. Yes?
What format will the exam be?
The formats it will be a mixed format. You can expect true, false, multiple choice, long answer, diagrams, all sorts of stuff on the exam itself. So with that, good luck with your studies, and we will see you next week.